So we can call this sequence A sub n, and the limit comparison test says grab a sequence you do understand, B sub n, and divide the two sequences. If the limit of the terms goes to some constant value like 1 or -1 or something like that, if it's not equal to 0, then they either both converge or both diverge. They match with each other. And that's why we pick a B sub n that we know, so we can make a statement about whether this sequence is going to converge or diverge. Usually in this course that's a P series, like 1 over n to the third power. We know that this converges. 1 over n to the second. 1 over n to the first, we said that's a harmonic series that does not converge. But P series are series that we do understand. We know they converge when that power is greater than 1. So we want our B sub n to probably be, let's say it's 1 over n to the p plus 1. That way we'll be dividing hopefully by infinity when we evaluate our limit as n approaches infinity. Okay, this is just a guess. I don't know for sure this is going to work, but we're going to try it out, and if it doesn't, hopefully that guess and the work that we do will help us modify what we do next time. But start with picking a B sub n that you understand, probably a P series in this course. And then let's do what it says. Divide the two sequences and take a limit as n goes to infinity. So here's my first sequence, 6 cosine 1 over n plus pi over 2. Very intimidating probably. It's just a regular old sequence. And I'm going to divide that, so that means I'm going to flip and multiply the P series I chose over there. And P plus 1, I chose that because I know that would be at least 1 power higher. So n to the P plus 1, divide by n to the P. They have the same base, so the powers would subtract, so you're just left with n to the 1. So we got n, and then I'll just multiply it to the rest of the stuff. 6n cosine 1 over n plus pi over 2. And then that all cancel out. Okay, so we're taking a limit as n goes to infinity for these terms. Let's see though, because as n goes to infinity, this would be 0. Oh, okay, this will be nice. As n goes to infinity, this term is approaching 0, right? So if you add pi over 2 to 0, then you've got cosine of pi. Oh, we still need L'Hopital's rule, actually. Cosine pi over 2 is 0. So this term is going towards 0 while this term goes to infinity. So to evaluate that limit, we need to use L'Hopital's rule somehow. Let me see what I can do. Maybe that means we need to go back and make it n to the p minus 1. But that's not guaranteed to be a P series because we don't know what P is. I could rewrite this so we could use L'Hopital's rule. We could say this is 6 cosine 1 over n plus pi over 2. This is all over n to the negative first. Right? If you have n to the negative first, you can make it be n to the first by kicking it upstairs, which would bring us back to where we were. And then when we evaluate limits of indeterminate form, well actually, okay, pause the video, make sure it was on the right track. So we can use L'Hopital's rule, and when I say equals, I always put with an L with the circle to say, hey, I'm doing, L'Hopital's rule. And the refresher on what L'Hopital's rule is, L'Hopital's rule just says if you're trying to evaluate a limit in indeterminate form, then it should be equal to the same limit after you take a derivative of the numerator and the denominator. So if I take a derivative of the numerator, the derivative of cosine is negative sine, so I got negative 6 sine 1 over n plus pi over 2. But then I need to multiply by the derivative of the innermost function because of the chain rule. So the derivative of n to the negative first is negative n to the negative second, right? This is n to the negative first. So the negative 1 power comes down, multiplies, and it gets reduced by 1. In the denominator, that negative 1 comes down and multiplies and gets reduced by 1. So Newton has set up this problem so that these terms perfectly cancel after one step of L'Hopital's rule. So no L'Hopital's rule in this next step. This is negative 6 sine 1 over n plus pi over 2. And now if we evaluate the limit as n goes to infinity, 1 over n becomes 0. 0 plus pi over 2 is pi over 2. So sine pi over 2 is what we're approaching as the limit goes to infinity. Sine pi over 2 is 1. So this is negative 6 times 1. This is negative 6. Okay, we took a p series. That's a series we understand. We made that our b sub n. We computed this ratio, and we found a limit that we were successfully able to evaluate. It's negative 6. So that means a sub n, b sub n both converge or both diverge. Since we know b sub n converges because it's a p series, that means a sub n must also converge. So all that work, we're now able to finally say that this converges. So it says, for what values does p converge? Oh, so the thing already said it converges. I kind of missed that. But now we can say for what values it converges. The sequence we chose was p plus 1, right? And so we said the harmonic series, where it's 1 over n to the first, that does not converge. This power has to be greater than 1. So it's tempting to say p is greater than 1, but the correct answer is p is greater than 0 because the p series we chose had p plus 1. So if p was just a little bit bigger than 0, this series would converge, and therefore this series would converge. So p has to be greater than 0 because 0 plus 1 would give us 1 over n, the harmonic series, which does not converge. If p is 1, 1 plus 1 is 2, so 1 over n to the second does converge.